Hello, everyone. Let's talk about using L'Hopital's rule to solve harder calculus problems. All right, so let's evaluate the following limit. We've got the limit as x approaches infinity of 2x cubed minus 6x over 7x cubed plus 7. What do we do? Well, if you directly substitute in infinity, you get a very obvious infinity over infinity. So we have a candidate for using L'Hopital's rule. So let's do it. We take the derivative of the top and the bottom, and we get 6x squared minus 6 using the power rules over 21x squared. Well, we plug in again, we still have an indeterminate form. So let's do L'Hopital's rule again. And we're going to get the limit as x approaches infinity of 6x squared minus 6 over 21x squared is equal to the limit as x approaches infinity of 12x over 42x. Well, plug in the infinity on the top and bottom again, you get an indeterminate form. And we could cancel the x's like we're used to doing, but I don't know. Why not do L'Hopital's rule again? So take the derivative of the top, you get 12. Take the derivative of the bottom, you get 42. And then you're taking the limit of a constant, and you get the constant. All right, let's do another one. This one's a little more difficult, I guess. So we're going to take the limit as x approaches 0 of 5 sine of x minus 5x over 6x cubed. Plugging in 0 gives us 5 times sine of 0 minus 0 over 0, an indeterminate form since sine of 0 is 0. So what do? We're going to take the derivative of the top and the bottom. Well, for the top, we know that the derivative of sine of x is cosine of x, and we know that the derivative of a constant times x is the constant. So there's the top. Then for the bottom, we just do the power rule. Bring down the 3, you get 6 times 3 is 18, and then you subtract the exponent by 2. You go all over, you get your 18x squared. All right, well, what do we have? Now we plug in 0, we get 5 cosine of 0 minus 5 over 0. Cosine of 0 is 1, so we get 5 minus 5. We get 0 over 0. So we still have an indeterminate form. So we can do L'Hopital's rule again. And that's what all of these problems are going to look like as I keep running through them. Give me 1 second. I had to plug in my charger. So yeah, let's do L'Hopital's rule again. So limit as x approaches 0 of 5 cosine of x minus 5 over 18x squared. We take the derivative of the top and the bottom, and we get limit as x approaches 0 of negative 5 sine of x. The constant term goes to 0, and the derivative of cosine is negative sine of x. And then on the bottom, we just do the power rule again. Bring down the 2. We get 36x to the first power. All right, what do we got? Plug in the 0. Still in indeterminate form. We get 5 times, negative 5 times sine of 0 over 36 times 0, 0 over 0. So let's do it again. And this time we'll get the derivative of the top becomes negative 5 cosine of x, because the derivative of sine of x is just cosine of x. And on the bottom, we get 36. Now we got something. Now we can just plug in the 0, and the cosine of x goes to 1, and we get negative 5 over 36 overall. All right, let's do another. So now we're going to do the limit as x approaches infinity of the natural log of 5x minus the natural log of x plus 1. So the first thing we're going to want to do is kind of opposite to what you might be used to. We're going to actually combine the logarithms to get ln of 5x over x plus 1. And then we're going to put the limit on the inside of the function and find out that we have an indeterminate form here. So plug in the infinity, and you get an indeterminate form on the inside. So we can do L'Hopital's rule on the inside and say that the natural log of the limit as x approaches infinity of 5x over x plus 1 is equal to the limit as x approaches infinity of 5 over 1, which is just 5. So then we get our final limit, which is just ln of 5. All right, here we go, another problem. So let's evaluate the limit. Limit as x approaches infinity of 5x squared times e to the negative x. And that's going to be equal to the limit as x approaches infinity of 5x squared over e to the x. I might have just said the same thing twice. Anyways, you know what I mean. Here's the problem. So plugging in infinity, we get an indeterminate form because infinity squared is infinity and e to the infinity is infinity. So we get to use L'Hopital's rule. Here we go. We get the derivative of the top. Nice little power rule application. And the derivative of the bottom just remains to be e to the x. Then plug in infinity again, and we get infinity over infinity again. So we could just keep applying L'Hopital's rule. And finally, we get a nice answer. We get derivative of the top and bottom becomes 10 over e to the x. E to the x just remains the same throughout this whole process because, well, that's how we define e to the x, to be the function that when you take the derivative of it, it's the same thing. So now, I mean, I could do, you know, a little magic and play around with some ln of x's, but I mean, the moral of the story here is that when you plug in infinity into the e to the x, it's some, you know, massive number, no matter how big the number you can plug in. So you get 10 divided by a massive number goes to 0. It's the basic idea. So there's our limit. All right, here's another one for you. The limit as x approaches 0 of 5x squared over the natural log of secant of x. All right, what do we got? So right off the bat, plug in 0. This gives us an indeterminate form of 0 over 0. And why is that? Well, you plug in 0 to the top, you get 0. Plug in 0 to the bottom, you get ln of secant of 0. And remember that secant is 1 over cosine, and cosine of 0 is 1. So then you get ln of 1, which is 0. So let's do L'Hopital's rule. Now we take the derivative of the top and the bottom, and on the top, we get a little power rule magic. Bring down that 2, you get 10, and then subtract the numerator by 1, and you get x to the first power. The bottom part's a little more complicated, but it's not too bad. It's just a chain rule problem. So the derivative of the outside is going to be 1 over secant of x, and then you multiply by the derivative of the inside, which is secant x tan x. And then you get some really nice direct cancellation of the two secants right there, and you're left with just tan x at the end. So we get another indeterminate form, 0 over 0. And the reason is because plug in 0 for 10 and 10x and it goes to 0. And then for tangent, recall that tangent is sine over cosine. So sine of 0 is 0 and cosine of 0 is 1. So you get 0 over 1 goes to 0. So we do the rule again, derivative of top and bottom. Derivative of 10x is 10, and then the derivative of tangent is secant squared x. If you don't believe me, it's pretty easy to derive. So we can work with this because on the top, you know, you get the limit of a constant, and on the bottom, you get 1 over cosine squared x, and cosine squared of 0 is 1, so you get 10 over 1 overall, and then you get 10 for the whole limit. All right, and our final example for the day, which I did not turn into multiple slides, I apologize. It's not too bad. So on the top here, plug in the 0, and you get that the e to the 3h goes to 1. Then it's minus 1 plus 3 times 0. You should see that this goes to 0. And then on the bottom, you get the direct plugging in of 0, and you get the indeterminate form of 0 over 0. So doing L'Hopital's rule, you get, yeah, the derivative of e to the 3h is 3e to the 3h, little chain rule action right there. do the derivative of this inside part, all that's left is the 3, and it turns into -3. And then on the bottom, we do a power rule, bring down the 2, you get 14h. So once again, we have an indeterminate form because you plug in the 0, and this becomes 3. And then you get 3 minus 3, which is 0, and then plug in the 0 on the bottom, and you get 0. So we can do L'Hopital's rule again. Derivative of top and bottom, the -3 goes to 0. And then a little more chain rule action, we bring out another 3 from doing the derivative on the e on the top, and you get 9e to the 3h and 14 on the bottom. Now when we plug in 0, we get that e to the 3h goes to 1, and we're left with a 9/14. And all right, that's how pretty much every L'Hopital rule problem goes for all of time. So I hope that this little demo here was a nice little example to help you understand the techniques. Have a nice day.